Welcome everybody to Calculus BC. In today's episode, we're going to be discussing Chapter 7.5, which is Strategies for Integration. And so there's not a whole lot actually to be learned in terms of this lesson, more like we're just kind of training our reflexes to be adept and to be prepared for whenever we see a potential situation happen, whenever we are integrating an expression. And so these are just some general guidelines as how I attack an integration problem here. So things to look out for. When faced with an integration problem. Okay. And here we go. Whoops, darn it. Did not want to change colors there. All right, so the first thing you want to look out for, just some questions you want to ask yourself. First off is, are there two things being multiplied? If so, do they have a derivative relationship with each other? And if that's the case, hopefully a tool stands out to you. That means that you should U-sub this thing, right? U-sub. Right, that's something that we have from Calc AB. So just U-subbing it if you see that derivative relationship. If the two things do not have a relationship and are being multiplied, that seems that it's very likely going to be integration by parts, right? Integration by parts. And so let's see. What we just learned in the last section would be, is this a weird-looking rational expression? Because if it is, I think partial fractions is going to be our weapon of choice against a weird-looking rational expression, right? And some other things that people tend to not think about, especially because we're in BC, it's been a long time since we've been in this precarious position. But can the integral be done geometrically? Or sometimes can it only be done geometrically? Okay? And then the last one, sometimes the simplest maneuver is the best. Is there any algebraic manipulation that can be done to make the integral more obvious? And these are just things that I tend to ask myself as I look through each integration problem. And again, we're just trying to look for a strategy for integration here. So what's going to happen in this video is we're going to look through 10 problems, and we're going to, just integrate all of them. And we're going to talk about which strategy was best and why. So here we go. Without further ado, if you need to pause the video, pause it right now, so that way you can write down these strategies, and then we'll move forward into our first example here. And so in the first example, the integral is x secant squared x dx. Well, I got two functions being multiplied. I do not see any kind of derivative relationship between them. If I saw like another secant tan x out there, maybe I could do a U-sub. If this was like secant squared of x squared, I might be able to do something U-sub related. But it doesn't look like x and secant squared x have any kind of relationship. So to me, this screams integration by parts. So integration by parts. Well, what is that? We just learned that last week. That's going to be u, du, and then dv and v. How do I do this again? Well, I got to pick a u and a dv, and I got to also not make the problem worse. Okay, so how do I do that? I'm going to select u as x. I could be wrong, and if the problem starts getting worse, I will back out and try it again. That means that dv has to default to secant squared x. I will integrate this guy up to become tangent. I forgot my dx there, and that's going to be 1 dx. Things seem to be on the up and up with this problem here. So remember, the integration by parts formula is going to be uv. That's going to be x tan x minus the integral of v, so tan x. And then du is going to be 1 dx here. So as I go to integrate tangent, I could remember its formula. But if you don't, this is actually a great time to practice U-subbing. because what I can do is I can integrate this thing as sine x over cos x dx to let u equal cos, du become negative sine x dx, and then that's my linkage right there, right? And so actually it's negative du equals sine x dx. So now I'm going to kick the negative all the way on the outside. Hopefully it's not too fast for me to say that ends up becoming plus 1 over u du, and then x tan x still here. Now at this point, I'm going to go ahead and integrate. I'm going to get ln of absolute value of u, but u was cos x the entire time. So I got x tan x plus this guy plus c, and that is my integral. Again, what led me to believe that this was integration by parts? Two things being multiplied, no relationship to each other. Let's move on to number 2. Let's take a look at this one. A definite integral. Okay, cool. Looks like there's going to be probably some plugging stuff in at some point here. Now from here, what am I looking at here? I'm not looking at a u sub, right? It's not like if there was like a 2x on the outside, this would definitely be a u sub, but that's not what we're dealing with. We're just dealing with this. It's not an integration by parts because, the derivative of this would be chain rule, and that would make the problem really bad. And then if I made 1 dx, an x would have to come out, and I don't think that's where I want to go. Well, this is something that you definitely want to be able to recognize on site. And as always, feel free to pause the video when I write a problem down. That way you can kind of guess to see if your intuition is correct. This is a geometric integral. We can only do this geometrically until we learn something called the trig sub. And even after we learn the trig sub, I would highly recommend you do this geometrically. This is a half circle. It's a half circle with a radius of 3, centered at 0, 0. Here you go. Negative 3 to 3. And now I'm going to go ahead and integrate this by finding the area underneath the curve, right? That is the point of integration. So it's going to be 1/2 times pi. The radius is 3 squared. 9 pi over 2. Simple as that. A little bit of integrated math, too, can help save the day on that one. So that's number 2. Again, kind of a weird looking one. These are definitely graphs we want you to be able to recognize on site. So let's move on to number 3. Number 3. Integral cos 4x rad 2 minus sine 4x dx. Okay. Well, what am I looking at here? I'm looking at a function, and I see its derivative on the outside, and they're being multiplied. So if I see a function and its derivative, I'm thinking it's our good old buddy u subs making their triumphant return. So 2 minus sine 4x, du is going to be negative cos 4x times 4 for chain rule dx. Kick the constants over to the du side, so negative 1/4 du is equal to cos 4x dx. That is my linkage right there. So now what I'm going to get is I'm going to get the integral of rad, not 2 minus 4x, but rad u. The cos 4x dx becomes a du. Don't forget about that negative 1/4 that hangs out on the outside. And I've got negative 1/4 integral of u to the 1/2 du, which is going to be u to the 3/2 times 2/3 times negative 1/4. Don't forget about him. Those guys will kind of cancel each other out. So I got negative 1 over, that becomes a 2, so negative 1/6. And then I've got u to the 3/2, but u was 2 minus sine 4x, and now to the 3/2 plus c. We were dealing with an indefinite integral on that one. Don't forget your plus c's. All right, let's take a look at number 4. Number 4. As always, feel free to pause. I know I'm going through these pretty quickly, but again, what was it that gave this away as a u sub? It's that we have a derivative, we have a function and its derivative present. I mean, hopefully that makes a lot of sense to you. All right, number 4 here. It's going to be the integral of dx over x squared plus 8x plus 7. Well, the first thing I'm going to do here is I'm actually going to make him 1 over x squared plus 8x plus 7. Well, I think I can factor the bottom, but there's not a whole lot else I can do with this. I'm going to go x plus 7 times x plus 1. And when there's a rational function, when I don't know what to do with it, I'm thinking, especially because the bottom can factor, I'm thinking partial fractions here. So on the side here, I'm going to say 1 over x plus 7 times x plus 1 is equal to a over x plus 7. Oops, darn it, I don't need that there. Plus b over x plus 1. Again, it doesn't matter what order the x plus 7 and the x plus 1 comes into. It ends up resolving itself. And you end up with 1 over equals a times x plus 1. So remember this from partial fractions in the previous video. X plus 7 here. Now, I can totally distribute the a and the b if I wanted to, solve it like a system or solve it by association. No worries there. I think I'm going to initiate risky business on this thing. So I'm going to say I'm going to let x equals negative 1. And if I do that, this guy's going to go away, and I'm going to end up with 1 equaling, looks like b times 6, right? And so I get b equaling 1/6. Okay, cool. Well, on this side, I'm going to let x equal negative 7. Again, risky business, right? Which means the b is going to go away, and end up with a times negative 6 equals 1. So a equals negative 1/6. Awesome. Okay, so now what does this allow me to do? It allows me to separate my fraction. I can uncommon denominatorize it, right? We talked about that before. And you see how I talked about how the order of the x plus 7 and the x plus 1 doesn't matter? Because b ultimately ends up becoming over x plus 1. And then, whoops, not 1, 1/6. 1/6 over x plus 1. And the a being negative, I just swapped the order of it. So it's minus 1/6 over x plus 7 dx. Before I integrate, I'll probably factor out that 1/6 because I don't like it there. And I think now I'm in a pretty good position to integrate this thing. I'm going to get 1/6 ln of absolute value of x plus 1 minus ln of absolute value of x plus 7 plus c. Or I can make this just a little bit simpler, and I'm starting to run out of space here, but I could make it a little bit simpler and call it 1/6 ln of x plus 1 over x plus 7, which is very likely the version you would see on your AP exam on your multiple choice. So there you go. There's a partial fraction for you guys. I'll be right back with a couple more examples. Give me 1 second. In this next example here, I want to give you one that's very similar to the last one, and I want to show you why this is not partial fractions here. And so this is going to be x squared minus 6x plus 9. So it looks like it would be, right? Especially based off of that last example, like, you know, totally partial fractions ready, especially because I'm going to kick out that dx right there. So now I'm going to get here. And so what I'm going to get here is if I factor the bottom, I'm going to get 1 over x minus 3 squared dx. But actually, this integral is pretty easy. Like, we've done this before. Like, this is Calc AB right here. I can call him x minus 3 to the negative 2. And now I can say that that's going to be x minus 3 to the negative 1 over negative 1. Technically, there would be rule chain, but in this case, the rule chain would be a 1, so who cares? And then plus c. So don't try to force partial fractions to happen if you don't need to, right? This time there was a duplication. It was a perfect square trinomial on the bottom, so I just integrate him. No big deal at all. Let's go and do another one here. Let's see. Oh, this one, number 6. Is going to be the integral of x minus 4 over x squared dx. Again, speaking of not forcing things to happen, right? This one here is not going to be a u sub. I have a binomial over a single nomial, so that's going to be the integral of x over x squared minus 4 over x squared dx. Whoops, x squared. And so that's going to end up becoming the integral of 1 over x minus 4x to the negative 2 dx. And there's a reason why I wrote it like that. It's because this guy's going to become ln of absolute value of x. Be careful, he's not x to the 0 over 0. And he's going to become, looks like, minus 4x to the negative 1 over negative 1 plus c. You could simplify that out to say ln of absolute value of x plus 4x to the negative 1 plus c, and that would be the result of your integral. So again, why did I not do any kind of u sub there? It's because whenever I have a polynomial over a monomial, I try to simplify it out, especially if that monomial is simplifiable. So a lot of this is just learning how to be loose with your with your integrals, and just kind of staying calm and knowing like what tool you're supposed to use, because they are definitely going to prompt you for it. This one here is probably the most deceptive out of all of them. This example 7 here. This example 7 is the integral of x squared over x squared plus 1 dx. You could long divide it, or you could do like this ridiculous kind of trick looking thing where you do this x squared plus 1 minus 1 over x squared plus 1 dx, where now you suddenly end up with x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1 dx. And then you end up with 1 minus 1 over x squared plus 1 dx integral, which gives you x minus tan inverse of x plus c. Now, if you didn't think you'd remember to do that, you could just divide the bottom into the top. You could say this is x squared plus 0x plus 1 divided by x squared plus 0x plus 0. And now you get 1, right? Because x squared goes into x squared. Then you get x squared plus 0x plus 1. By subtracting the whole shebang, these guys go away. You end up with a negative 1. And so you end up with 1 minus 1 over x squared plus 1. I hope that situation looks familiar. So you could use long division on that one if you end up in that precarious position. Let's see here. Let's do another one. Number 8 here. A definite integral. We haven't seen one of these in a long time. The square root of x squared minus 4x plus 4 dx. You know, I'm not seeing a u sub here. I'm not seeing any kind of thing on the outside. I definitely don't think that's an integration by parts, because I'm not going to make that u, and I'm not going to make that dv. So what I'm going to do is I'm going to go and factor the inside. And what I get is I get x minus 2 squared dx, because it's a perfect square trinomial. These guys are going to cancel. And I end up with the absolute value of x minus 2. Please don't forget that absolute value. Now at this point, you might be tempted to make a piecewise function and say that it's the negative version of x minus 2 when x is less than 2. And it's the positive version of x minus 2 when x is greater than or equal to 2. And then you integrate from 0 to 2 of the negative version, so I'll just call them 2 minus x dx, plus the integral from 0 to 2 of x minus 2 dx. And you'd be tempted to do that, and it would be totally legit. Except, whoops, not from 0 to 2, 2 to 4. That's what I meant, 2 to 4. Except this would be bad. You don't want to do that. You don't want to make life harder for yourself. This is one that absolutely can be done geometrically. This is a v function centered at 2. And you're going from, your limits of integration are from 0 to 4, so you've got a little bit of integrated 2 in your life. 1/2 base times height, so the base is 2. The height is going to be what happens when you plug in a 0, you get 2, plus 1/2 base, which is 2, the height, which is 2. Awesome. So what you get is you end up getting 4. And so that problem can be done pretty quickly as long as you don't overcomplicate things. Couple of different integration techniques that I want you guys to still be aware of. So remember, when it comes to the integral of something like, this is number 9 here, the integral of something like secant x dx, this is actually a u sub, right? So you're going to multiply them by secant x plus tan x over secant x plus tan x dx here. So you get secant squared x plus secant x tan x over secant x plus tan x dx. U becomes secant x plus tan x. Du ends up being secant squared x for the derivative tangent, and then secant x tan x dx for the derivative of secant. That becomes your linkage. You end up with the integral of 1 over u du, which ends up becoming ln of the absolute value of secant x plus tan x plus c. Now, if you happen to have memorized that at this point, good for you. But this is the, and I'll take that on the test if you just go straight forward, but also keep in mind that that u subbing it is also an option in case you forget. Last problem I want to do for you guys is number 10 here. which is going to be the integral of x rad 4 minus x dx. This one here is a little bit odd. It's definitely a u sub. And let me show you what happens here. 4 minus x is u. du is negative 1 dx, which means negative du equals 1 dx, which is your linkage here. And you get the integral of x rad u du with a negative on the outside. The problem is that this x is hanging on the outside. And so usually it happens under these situations, but when you see this, you end up having to do an x sub, where you end up with having to solve for x here. So I'm going to go and move him over. So x plus u equals 4. So then x equals 4 minus u. And that's what goes in for x here. So I end up with 4 minus u times u to the 1/2 du. This can distribute in. I end up with negative integral of 4u to the 1/2 minus u to the 3/2 du. And now I've got the negative total integral of 4u to the 3/2 times 2/3 minus u to the 5/2 times 2/5 plus c. So the negative version of 8/3 looks like, what was u the whole time? 4 minus x to the 3/2 minus 2/5 4 minus x to the 5/2, and then plus c, like that. And there you have it. There's just a big, bad summary of integration techniques. Lots of integration. You're going to be doing a lot of it in your prep book tonight for your homework. So just keep a flexible mind. Ask yourselves the same questions. You know, the multiplication relationship. Is there one or isn't there one? Can it be done geometrically? Any algebraic manipulation you can do? Is it a weird-looking rational expression? Any of those, that will lead you to the direction of the integral you want to take. So hopefully this makes sense. As always, please leave questions or comments in the comments area. I will see you all in the next episode.